Hello. Good afternoon, everyone. I would like to invite our next speaker, Mr. Rajesh Vasa, Professor Rajesh Vasa. Professor Rajesh Vasa is an innovator and an entrepreneur with over 2 decades of experience spanning both industry and academia with a specialization in AI and complex software systems design. He leads the transitional research at the Applied AI Institute of Deakin University. His recent current work spans multiple areas: building intelligent homes, assessing clinical risk from medical data streams, improving patient care in hospitals, analysis of data from complex simulations, conversational agents to work in educational settings, and analyzing data streams to improve productivity in various settings. His core research is in constructing robust AI. He's going to be talking to us about how to leverage AI and the opportunities and the challenges. Welcome, Professor Rajesh Vasa.
Thank you. So I'll start right off. Hopefully you all can see the screen and it's all clear. So I've titled this as a conversation in AI. I didn't know the background of the audience, so I'm going to take it from the assumption that we have to just set some stage. So this, just looking at the talk so far, I think this part is very clear. Everyone knows that this whole space is exploding. A lot of people are saying we do AI, but interestingly, this is the current story of the day. In that we know that AI is good when you have good data, and the domain doesn't change too much. Some quick examples. So that woman's face is completely generated. We've got medical applications saying that they can do amazing things. The interesting thing is most of the best AI is completely hidden. So Google uses quite a lot of AI, and it's not quite clear to people that this is the most stable form of AI per se. So map search and Google search itself uses a lot of context-aware information retrieval related work behind the scenes. The most common question I get asked is, will AI take my job? So I set this in there just primarily to just set the stage, saying that AI will not take the job. And this is just a screenshot of, this is a picture of what the people in a ship do and what they used to do a few hundred years ago. And what's happened is that the person who's looking out has changed. They just use more sophisticated tooling, but as such, AI is unlikely to take a specific job, but it will certainly transform jobs. There's a number of different definitions of AI. I'll go through this fairly quickly just to set the stage more than anything else. So there is a school of thought that says AI is about an appearance of intelligence. There's another school of thought that says that AI is something that only till recently humans could do and machines couldn't do. This definition also means that once a machine can do something, we'll no longer call it AI, of course. And of course, this is the textbook definition of AI, which says that it's got something to do with reasoning, learning, and problem solving. Ironically, machines cannot do reasoning very well. They certainly can't do any sophisticated problem solving. Then they can barely learn. And that's the focus that I'll take for my talk, is to show how difficult it is with machines when they do learn and where some of the research challenges are. So this is a quick example of the key things that AI can do. One is it can predict, it can classify, it can learn behavior, sort of. We can do certainly searching, we can optimize, and we can act using some rules. Almost all of these things, all 5 of these abilities are in a self-driving car. So a vision system will classify some objects. There's a learn prediction system. There's a behavior learning module. There's some form of optimization happening behind the scenes. There's searching, and then there's rule-based systems that say you can drive at a certain speed. Because the rules obviously are made by humans, and it's sometimes easier to just set the rule rather than get the machine to learn it. So this is just to purely set the stage. So what is the big deal with AI and where is the big mess? So if you took the classical description of what machine learning is, what AI is, there's this big diagram here where I've just got the learning component. And once some learning has happened, I can use the input, model, and output. This part is how I would normally use it. Now, almost all of the research that people are hearing about, it focuses on the machine learning algorithm, and they say, oh, look, we've improved this algorithm by 5%, 10%, 12%, 2%, and so on and so forth. Ironically, that's not where the difficulties are right now. So where we are focused on these days is, what did the machine actually learn? Because we're never sure 100% of the time what it learned. What data did it use to learn? Again, not quite sure about that either. We don't know if the prediction is useful. We don't know if we made the right assumptions. So these are the four big challenges. Broadly speaking, we would call it the misspecification problem, but without going into the academic lingo of why these things are challenging, in effect, everything but the machine learning algorithm is where all the problems are on whether we can actually take advantage of AI effectively in practice or not. So what I'll do is I'll shift to give you some examples. Say if I showed you the data stream like this is the dam level, water level in Melbourne Dam, where we get the fresh water. Melbourne is where I'm based currently. And if I said, okay, just tell me whether this month I'll have enough water based on this, can a machine learn something? The machine certainly can learn. The thing is, if all it has is historical data, the range in which it'll make the prediction is going to be very broad, because the minimum was around 30, 40% in August, and the maximum was about 80%. So the entire range is what it'll learn from. I can't get hundreds of years of data because this data only existed for about 20 years. And the sensors that were collecting this data were recalibrated 5-6 years ago. So they're certainly measuring differently. They've added more dams, therefore the percentages changed. Almost all of that knowledge doesn't exist inside any AI model. The other thing is, the ML doesn't know what it's looking at. It doesn't even know this is called the thing that this fluctuates based on rainfall data. All it knows is this moves up and down across some seasonality. But the reason why this moves up or down is not something that the machine will know about. And that's something we have to provide. And the number of things we have to provide like that is quite large. So if I asked a simple question right now to any weather forecasting algorithm, will it rain in the next 3 hours? It can say one of those three, but it doesn't know why I asked that question. Why does that matter? Because I might want to paint a fence. And if I'm painting a fence, I don't want any rain. But if I'm taking the dog out for a walk, or I just want to go for a walk, or I want to water the garden, those answers might change how I decide to do something. And this is the kind of matrix internally that it will give you, which is quite sophisticated. And so it's not a single value that it makes a decision from. It's actually a more sophisticated distribution. What currently is happening in most AI systems is they're flattening it, averaging it, and picking a single point value, rather than an entire distribution and entire decision frame that we need to do anything really sophisticated. So when humans make decisions, they need the entire decision frame and appropriate training to understand what it means. So from now on, I'll effectively switch the talk to talk about that particular aspect of it and why this is a specific challenge and where we need to start looking at it. So AI systems are designed to serve humans. And the first question is, let's say I made a machine and I say I can do something, but the human cannot do it. We don't know whether it actually works. For us to know something works, we have to at least be able to do it. We may be able to do it slowly, and the machine can do it fast. But even if it does do it, the way we define it works depends on political, economic, as well as the engineering and technological limits, not purely an engineering problem, in other words. Right now, we don't have a clear definition of it works. So which means if you can't define it's working within a certain boundary, we don't know when to fix it. We don't know what the quality attributes of it is working are, because we really quite don't know how the machine is learning and what it is learning with any level of precision that matters. And the way we evaluate, mostly it's happening in development or in research, but in production, the metrics are different. And there is an entirely political dimension and there's a business dimension that immediately enters there. And we don't know any of those things. So it's a lot of the work that we see right now, I would say, is very advanced research, early translation, but some of the more pertinent aspects of AI, which is how do we know it's actually working in a way that is acceptable, is yet to be figured out. So as an example of what an AI system would show you, this was from a few years ago, but it's still more or less relevant because what's happened in the last 2 years is those percentages increased a little bit. Now in this diagram, there's an elephant, which is classified as a chair, top left-hand corner. And the reason why that happens, it still happens, is because the machine has never seen in all of its data an elephant in a room. Therefore, it never expects one. And it's a context problem because machines are learning in context. The other thing that also happens is if I had to make a decision about books, at what percentage is a book a book? 50% a book, 20% a book, 30% a book? And those percentages are very dependent on the data that was used to train it. So if I had to do something related to books in this photograph, I would have a lot of difficulty in being confident because the confidence value also depends on the underlying data stream. And most AI developers don't specifically know what data was used to train their data sets. And I'll get to that next. The other thing is, say if I showed you a piece of text like this that a machine wrote, and if I said, is this good to put in an article? Strictly speaking, the grammar is correct. Vocabulary is correct. There are no spelling mistakes. But both those paragraphs are utter nonsense, though, strictly speaking, semantically accurate, but meaningless. So each sentence is grammatically correct. It just doesn't have any meaning. If the intention is to do some comedy, this would be perfect. But that's generally not the intent. We want to write articles with it. And this is from last year. This year, it's slightly better, but not that much better that I can definitely say that this is ready to go. It works, it's perfect. So there's a lot of sophisticated work still yet to happen. And the reason why that happens is this is the kind of training data set that is currently used to train data. These are not things I'm making up. These are labels that are actually being labeled, often in low-cost countries. So India, Vietnam, South Africa, somebody sent all these photos and they'll say, classify against these criteria. Now, some person decided loser, failure, non-starter is a label worth having. Again, we don't know who decided it. It just happened to be there. It's always been there. And then they asked to classify it. And then somebody makes a choice that this is what it is. This is the definition of loser, second-rated, and mediocrity. Again, who decides it? Some random person is asked to do this, and they're paid a pittance to do it. So this is the ImageNet data set. And almost all the data sets are similar in their ability. This is not unusual, by the way. And this is how the ImageNet image classifiers are working. So things like face detection, fine. But if you're doing anything beyond that, it's interesting. So there is even a sannyasi, beggarman, all kinds of wonderful things in there. The other thing is there's a lot of assumptions being made around emotions. Most emotions are trained on these 6 faces, fixed faces, photographs, not videos. So some researcher a number of years ago decided that there's only 6 emotions, which can mysteriously be captured by a Japanese actor, 6 of them, or 7 of them, I think. And they're a perfect proxy for every human. Look, they're okay if you're trying to do kid-based level, but anything beyond that, this is very sophisticated because the underlying assumption is the facial expression captures a lot of depth. And this kind of assumptions are encoded into every tiny nuance of almost all machine learning models right now. The reason I say that this is a mess is because data alone isn't enough. You can throw the data and the machine will learn a pattern, but the data has no meaning. And the meaning comes from humans. We have to give it the context. And if I don't give it the context and I don't give it the meaning, it's just a pattern detector, which is completely meaningless because a pattern detector alone isn't enough to make any sophisticated decisions. It will detect a pattern. We then collapse it without a distribution on it, and it gets into a lot of difficulties afterwards. So give you an example of this. If I said, look, here is a self-driving car, it will brake at a red light, but once every 1,000 times, it won't. Is that adequate? Roughly translates to once a year, it may not stop at a light. Some of you might say, oh, it's not too bad. Many of you might say, no, not acceptable. And then I could say, is it once every 10 years? Is it okay? At some point in time, you might say it's okay. But right now, we don't even know what that number is. The other thing is the data that we use is highly targeted. So I can only use speech data to make a speech recognizer a bit better, wind turbine data to make wind turbines better. But speech data doesn't help me with wind turbines. This means that I have to select lots and lots of data for specific adaptations, set all the data, set all the context, and so on and so forth. So this whole work is yet to happen. And remember, we still don't know what the machines are learning and how they're learning, which tends to be an issue still. Machines fail, and when they fail, we have to build for the cost of failure. So if a machine makes a mistake, there is a consequence of that mistake. And that can't be something we can avoid. I can choose to ignore it. I can choose to let the user know. But if I'm letting the user know the machine's failed, it means that I have a definition of failure. And the machines don't have a definition of failure. They just have a probability of a guess. Somewhere along the line, I have to say this guess at this probability is not good enough. But that probability is not a fixed probability. So there's more dimensionality to it without getting into the detail. But these are the kind of problems that most of us researchers are looking at and looking to solve. The other thing is this is more of a pragmatic choice. Is it a feature or a function? It's not clear for a lot of people. By and large, most of the AI right now is not functional. It's purely a feature. A feature is something like a cup holder in a car or a radio in a car. It's not the primary purpose of a car. Yeah, the primary purpose of a car is not to play songs. The primary purpose of a car is to move people from A to B safely. As long as they do it, people are happy with it. Is AI a primary function of where it's being used? And if so, if I took the AI out, will the product not be that product anymore? And given the state of AI, we are still in very early days when we are introducing this technology, along with all the risk. The other interesting thing with AI is I don't know if it's useful till I try it. So if I want to know if a face recognition is accurate enough and sufficient enough, I literally have to put it into production. And we've done some in India like that. And it's an 18-month process to figure it out, if it's good enough, if it actually adds value, if it's a bottom line and the profit is acceptable. There's no other way. You can't do this in the lab because the data you need doesn't come in the lab. The other interesting thing with this is that we need a new methodology for building AI systems. Almost everything we know about how to build traditional software doesn't work. And almost everything we know about how to build traditional technology doesn't work. Because the prototyping can be done in a few months. This is what most people are seeing is the prototyping phase. They're getting very excited by it. But the hard part is the evaluation can take many months to know if it's working in practice. And putting it into production use can take a year, up to a year, because almost everything has to be redone. We rediscover some of the requirements, the edge cases we missed. We may have to go and fix many things. We may have to fix the data. And then again, we have to go through the whole process multiple times. This process is not overall that quick. So there's a lot of research on how to speed this up, of course, that we're currently looking at. This part's clear, and it has always been clear that we need a different methodology, but we don't have good answers as yet. And there's a group of people looking at how to speed this up so we can take the power of AI into many domains. Beyond a few small niche areas, it's not quite effective yet. The other thing is the economic cost of AI is very high. The cost of computing is low, but the issue is when they make a mistake, we don't know the consequences of those mistakes in all domains. And we don't know yet. So that ends up meaning that I'm taking an option or an insurance cost that I don't know about. The risks are unknown. And we don't know when that it works and it's good enough point is, except when we start doing it. So we have to run experiments in production, wait for it, and slowly get all that in place. Again, these are all focuses of serious R&D right now. And this is where the reason why this whole talks may seem negative is purely because some of the limitations is what I focused on. All the other speakers, I'm sure, would have said it's amazing, it's ready to go. So the common question is, when will it be ready? A probabilistic system, a good example is radar. It started in the 40s. Took till the 60s before it started to be effective and useful. People were using it in the 40s because it was better than nothing. And AI may be like that. In some areas, it may be better than nothing. It will require new support, new operational skills, new techniques, new methodologies. And when it went into military, we had to develop strategy, tactics, and integrate that more effectively through the process of warfare. Similar things will happen in AI, with AI and business. A lot of businesses don't know yet how to use this technology. They're just seeing early versions of it and they're getting excited by it. But we have a long way to go. So this decade would be the decade where we learn how to use this more effectively. It's much like e-commerce. When it first came out, very early days, we didn't know how to scale it. We never got Amazon and Amazon Prime in the 90s, early 90s, or even 2000s. It took nearly 15 to 18 years before we knew how to do the logistics to power e-commerce properly. So some of the key focus of where the AI is, how to scale it, figuring out what the value is, realizing that data is not enough. We need the right subject matter experts integrated into the AI workflow. We need a different methodology to build this. Things fail, we now need to know how to deal with it. The utility can only be figured out in the real world, which means the business case has to be constructed differently, and the funding has to be done according to that. People don't know whether it's a feature or a function. It might start as a function, it might start as a feature and become a function, but it'll take time. We quite still trying to figure out how to evaluate this technology, and we can't cost it as yet. A lot of this, if it sounds like early stages technology, very R&D, exciting, let's go do it, that's essentially where it's getting used. Any large, serious business will take their time, and rightfully so. I mean, if you used AI to decide whether you get paid or not paid, or it's a probability of how much you're going to get paid, I'm sure most people wouldn't be very happy. In case all of this sounded extremely negative, I want to close on an anecdote as to why it is like that. Is sometimes it's good to know what to do and what not to do. And that's my talk.
Thank you, Professor Rajesh. There's one question from the audience. How will AI help in the medical field?
Right now, AI has very minimal use cases in the medical field because the clinicians don't trust it. So it's R&D, and a lot of R&D is currently happening. But in the next decade, more likely use case for in the medical field would be in discovery of better medications, because it's more an optimization problem. But anytime you have to make a prediction that a clinician has to accept, the quality of the predictions are not robust enough yet. So it's unlikely to be widely accepted. IBM bet the farm with Watson on medical AI prediction, and they've gone bankrupt practically. Their entire division is shut down. It's not doing it anymore. So it's hyped up, it's overhyped up, but there are no clinical use cases that I have seen where it works.
There's another question what risk do you foresee in the way data is collected now?
Any data you collect is toxic. So if you treat data as a toxic material like radioactive waste, it's a better form mentally to consider it. So don't collect any data you don't need. And if you collect data, data collection is cheap. Labeling it is expensive. And labeling it in context is even more expensive. And in corporate or any world data sets, it's extremely messy because we can make numbers up. We might say number 3 means something, right? Number 3 means high risk, and number 2 means low risk, and number 0 means something. 4 days later, we might change the meaning of number 3, and so on and so forth. The machines don't know the way we change and interpret data. We change, so we interpret it differently, but the machines don't change like we do. So we have to then retrain everything. So that's where a lot of the issues are. Now, the reason why people get excited when they see face recognition or it recognizes a car, and it's uniquely there because the shape of a car has not changed. It's more or less a car as a car as a car. And if it doesn't detect the car, it's not the end of the world. But if you had to bet your house on it, you wouldn't do it. You would not use this technology. So it's early days, worth doing it, but also good to be clear about it.
Right. I think that's it. Thank you very much, Professor Rajesh Vasa, for spending your time and giving your valuable insights on how we can leverage AI.
Thank you for the opportunity.
Thank you.